think I have had the opportunity to meet the majority of you, but there are some of you that may be new to this, so I'm going to go ahead and give you a little bit of an overview. We had met originally in the Oklahoma City area and in the Tulsa area, and had invited all of those cities that were interested at that point to participate in an initial seminar. And at that point, we kind of gave them an overview, a more intensive overview than I'm going to go through today, of what the program components were, what it was about. Some of you were in attendance at that, and some of you were not. So just for the benefit of you that have not had a lot of access to the program thus far, we'll go through that a little bit. My name is Anita Gordy, and I'm director of what we call the Technology Resource Center here at OSU Okmulgee. We have 3 other people working on the project. Mike Jones is an architect, Ed Stone, and Charlie Cruz. So you'll be working directly with these 3 people also. They'll probably be doing more of the field work, particularly Mike and Charlie will be doing more of the field work than I will be. I'm kind of at the marketing, promotional type of thing. So once we get this going, Mike and Charlie will probably be working more of the technical side of it. So if you have any of the technical questions, you're out of luck if you're asking me. You'll have to wait until Mike and Charlie and Ed get to their portion of the program. This is the second phase of the program. Initially we did a program called CEMP, C-E-M-P. It didn't have the education component in it. We used 3 cities for the pilot project, Ada, Okmulgee, and Enid. They were picked by Commerce, who is funding the project. It's funded with the Exxon oil overcharge dollars. The first phase was, and this phase is also. What they were trying to see was if they could find some way to effectively use the Exxon oil dollars. They were getting a lot of flack from some of the areas in Oklahoma that felt like maybe the dollars weren't being spent as effectively as they could be. So they were particularly wanting to target rural areas. Now, as you'll notice at this point, some of these cities are not necessarily in rural areas, but what they were asking was that we target populations of 3,000 to 20,000 for purposes of the program. The initial phase with Ada, Okmulgee, and Enid, this took place, I think we started this program about 2.5 years ago. What they were wanting to do was pick cities with populations that varied, and they were wanting to see if maybe there were some things that were kind of in keeping with the population of the city. So that when we got to a phase of doing technology transfer, if we didn't go beyond this pilot phase, we could still share the information with other cities throughout the state. So we finished that program in February of this year with those 3 cities. We did provide a technology transfer conference in February that all of the cities throughout the state were invited to. We didn't have as good of attendance at that as we would have liked to have seen. But when we started marketing the second phase of the program, once we got funded for this, we were marketing to cities 3,000 to 20,000 throughout the state of Oklahoma. Initially, the thought was that we could probably take up to 20 cities depending on the population. What we have done at this point, the program was not filling, and we were having some of the cities that were over the population size were asking whether or not they could participate. Well, we were having to hold off and see whether or not the program was going to fill with our primary target audience. But we did go ahead and get approval from the Department of Commerce to go ahead and take in the city of Bartlesville. So Bartlesville is going to be represented in this program. To date, I think we have 11 cities that have showed support for the program and are going to participate. A lot of cities have not submitted the complete application packets yet. So we're going to be needing to get those together rather quickly. So if there's some concerns at this time, we've kind of tried to build into the schedule some time for you all to talk with us, talk with Mike primarily about maybe some of the concerns you're having with collecting the data and all. Let's see. Anyone driving a cream-colored Chevy has left their lights on? The city of Bartlesville has left their lights on.
I think so.
Okay. That'd probably be beneficial.
That's why they're taking the course.
Right.
Yeah.
Energy management. Okay. Let's see. What we might do is briefly go through the agenda. Let's see. We're starting a little bit early. give you an idea of what's going to be covered today. Let's see, we've got the coffee and donuts covered. I'm going to give you a program overview in just a minute. And then Mike and Charlie and Ed will go through the rest of the agenda for the day. Have all of you made arrangements to stay at Silks already? Have you, or at the Best Western? Have you had any problems with that? Okay, it's right out here, about 2 miles away. So that would be what we would suggest for your overnight stay if you need to call make reservations or anything. We are going to give you an opportunity for an informal reception, which will be held at the Best Western. So some of those questions and all you might hold until afterwards, after today's seminar, and might get a chance to talk with some of the guys a little bit with some of your informal questions. Tomorrow we're going to try to finish up by 5 o'clock. We're going to start a little bit earlier, but try to finish up by 5 o'clock. So hopefully we've got a lot of material to cover, and I'm in hopes that everyone can stay for the full 2 days, because it's going to be difficult to get it in that amount of time. But, okay, let's shift back to this. Like I said, we are the contractor. Oklahoma State University is the contractor working with Oklahoma Department of Commerce. This is the second phase of the program. We're targeting cities 3,000 to 20,000. This is our principal goal, to establish a community-based infrastructure development and technical and educational assistance program which will provide cost-effective solutions for rural local governments' energy use problems. That's kind of a fancy way of trying to get in everything that we want to say about this program. What we were finding with the first program, when we were just working with 3 cities, was that the local energy officers, a lot of times, were not doing as much of the work as we would really like to see them doing. Not only did that put a burden on our technical staff, but it wasn't as beneficial to the cities. Because when we were gone, you know, it was a little bit more difficult. If they hadn't compiled the data themselves and been really involved in the process, chances are it would be easier for the ball to drop once we were gone. So the recommendations that we made and all, you know, we would have concerns whether or not they would be followed through with. So we're in hopes, as you can see by the application package, we're putting a little bit more emphasis on the city collecting some of the baseline data and submitting the information to us rather than us going in and trying to do all of it ourselves. And that doesn't necessarily have to be a real technical person. It doesn't have to be a city engineer or something, as you've seen. I think, well, we have a city librarian that, from what I understand, is doing a very good job on this. So I think there was some misconception at the start that it maybe had to be a very high-level person. That's not necessarily the case. More times than not, it's a person that coordinates the effort. They don't necessarily do every bit of the work themselves, but they pull from different sources and pull the information together. So, accomplishment of program goals. The first thing we did was identify the local units of government that were willing to participate in the program. We did go through an intensive program marketing this. It was a little bit more difficult than we anticipated. We did press releases, we did personal visits, we spoke at several different meetings when we got the opportunity to, if there were city council meetings, if they were the municipal league meetings, just whatever we could. We tried to get on everyone's agenda. So all of you have been probably recruited in different ways. We were just pretty much following up on any leads we got, any calls of interest that we got. But the major thing that we had to see was that the city was committed. Just pure interest wasn't enough. We had to see that the cities were committed to doing at least their portion, meeting us halfway. Because if not, if we're going to work with 11 cities with the same team as we worked with last time, you know, we've got to have the cities be committed and do their share of the work. The second thing, designate the local energy officers. I think most of the cities have already done that. We haven't received the actual application packages from some of the cities, although we have talked, the contact persons from the city have told us who they are designating as the local energy officer. In some instances, they're designating more than one person. They're designating maybe a local energy officer and an assistant, so that it's not so much of a burden on one person. And that's fine. That's fine. We had asked that the cities, if at all possible, if they wanted to send more than one person to this seminar. That was great and wonderful, and we encouraged it. So, organize the energy management advisory committees. I don't know that all of the cities have done that yet, but hopefully, just like the local energy officer, this advisory committee is going to have input into the process as we go. And once we're done with the process, hopefully they're going to follow through and make sure that something is done with the recommendations that we make. Not only that, but we're going to get to points in the program where there may be a fork in the road where we could put more emphasis on one project than another. And it would certainly be advantageous to have input from the community, because we're a neutral party that knows nothing about your community necessarily, what's in the best interest. Like, for instance, in Okmulgee, when we were working with them, they had a historical site that, from an energy management, energy conservation standpoint, it would have been a total wash probably, but they had motives other than we would have seen if we hadn't had an advisory committee to guide us toward that. So hopefully it's going to represent different interests of the community that would blend well as well. Okay, provide energy management and monitoring education to the participating cities in energy accounting, commercial building energy systems, energy audits, your water and wastewater treatment plants. This is not including your plant process equipment, energy management and monitoring procedures. That's what we're doing today. That's part of what we're doing. So Mike and Charlie and Ed will go through more of that than I could touch on. Provide the technical assistance to the participating cities in the development of a comprehensive energy management plan. That'll be the next step, what we'll build on after this seminar. That's what we'll start working toward. That's where we go out in the field and we start working individually with each city and working toward what works best in your particular situation. I won't go into the actual steps there. You can read those yourself, and they're in your packet. Provide the information on potential financial resources available for project funding. That's probably going to be towards the end of this project. That's what you're going to want to know. Okay, we have all these wonderful recommendations now. What do we do with them? A lot of them are going to be low cost, no cost implementation things. And what we would suggest from our findings with the initial 3 cities that we've worked with is that you go ahead and implement the low cost, no cost types of things that you can do that aren't going to require major funding resources. And then from the savings that are generated from that, you stockpile those savings and use them on the major projects. But of course, you're still going to want to be looking at alternative sources of financing. What we're seeing at this point with the initial 3 cities, the Department of Commerce is going to be providing them with a direct grant. It's kind of a minimal grant compared to what they could use to fund a lot of these projects, but it's kind of an incentive for their initial participation in the project. What they'd like to do with this phase of the project, and which is on the drafting board, is set up a revolving loan, maybe even a 0 interest rate on quick payback types of projects for the cities that participate in this. So we're in hopes that towards the completion of this phase that they'll be able to do that. But that's what one of the plans is. There's also other types of financial sources that we'll discuss later on in one of the additional training seminars. We'll actually bring in people that do work with cities on providing different types of financial resources and leads that you can track down. And the last thing we'll do, we'll provide the final reporting and technology transfer activities, just like we did in the first one. You're going to want to report the findings, and what is probably beneficial is not only the findings for your city, but the findings from the other cities as well, because you can probably learn from those too. So we will provide that at the end of the project to you and to the Department of Commerce. So that's just kind of a quick overview for some of you that may not have been involved in the initial process. So as I can see, I know it's a concern to me. It seems a little bit hot in here. So we've called in our expert, Ms. Davis, to go ahead and change our thermostats. Okay, any questions at this point before we go ahead and move on? All right, who's up first? Mike, are you up first? Or? Okay, Ed, you're going to do the first portion.
first portion we're talking about is definitions and energy fundamentals. And they really go hand in hand. There's quite a list of definitions. We'll be referring to a lot of different words, phrases, and different things, and we've thrown these definitions in here just as a help. So we'll just refer to that as we go through. Under basic energy fundamentals, what this program is referring to, our charge is to save energy. A fallout from saving energy, of course, is you do reap the benefits of the dollars associated with the energy. And in many cases, there are opportunities to save dollars that won't necessarily save energy, and we do find those as well, but we're primarily trying to concentrate on how you can conserve energy. On page 27 is where I will start. Basic definition of heat. It's the basic form of energy, and the engineers like to refer to it as a symbol Q. That's just a definition. It's usually measured in British thermal units. 1 BTU is approximately equal to the heat given off by 1 match. Technically, it's the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. That's a BTU. All of our air conditioning tonnages in cooling loads and heating loads are in America referred to in terms of BTUs, 1 ton being 12,000 BTUs. You buy your gas for your building in terms of million BTUs. Mass is a measure of the amount of material in an object. It's relative, as this little diagram shows, it's relative to the weight. Density is mass divided by the volume. You get into considering mass in the relationships that we're talking about having to do with time constants in buildings, and a building that's lightweight, even though it may have the same heat transfer characteristics, a lightweight building will swing in temperature much more than a heavyweight building just because of the mass of the building and what's in the facility. Specific heat has to do with how much energy can be contained in a given unit of mass. And as you can see from the chart there, water as opposed to rock or concrete. So there's considerable amount of heat storage capabilities in various materials. Page 30 is getting into the basic equation of heat transfer, where in engineering terms we refer to this as we would call it m dot C sub P delta T. This says Q is the energy is equal to the mass or mass flow, depending on how you're dealing with it, times the C sub P, which is the specific heat, times the delta T. How much energy might be contained in a volume flow of air? If you were calculating an air conditioning heating requirement, that equation comes into play. Now, that's the basic equation, but for water or for air, you have to work it further into other forms. But that is the basic equation for energy flow through air or through water. The little diagram shows that basic equation, and these components work together to create a number that's calculated in terms of energy. Resistance, page 31, resistance value for the wall. we're talking real basic terms here, and I hope I don't know whether to move on quickly or not. The basic form here in resistance, as you would all relate to, of insulation in the wall of your home, you can see from the little diagram that each element of the wall adds to the resistance value that's created in the wall. When you look at the numbers, though, the most significant would be the R3, which would be the insulation value of the insulation in the wall. That is, whereas R1 might be 0.17, R3 would be probably between 11 and 19, so there's a relationship of 100 times difference between the resistance of the film as R1 to the resistance of the insulation in the wall. Those 6 elements comprise most all of the typical elements as you would calculate resistance value. Now, when you're looking at your buildings in the city, you would observe the wall and how it's built, when it was built, the dimensions, how thick the wall is, and you'd have to evaluate when you're calculating and giving us the information, what is that insulation material? Is it 3 inches or 2 inches? Is it fiberglass? Is it foam? Is there nothing there at all? A lot of times you'll know from when the building was built. It's very likely if it's in the 30s, there may be absolutely nothing in the wall but airspace. But when you're doing an audit of the building, you need to try to know and determine whether you, sometimes we even punch a little hole and probe the wall to determine what's in there. But it helps us to know later on if there's no insulation in the wall that you can add a blow-in foam or something to help reduce heat transfer in the building. The page 32 discusses the basic heat transfer methods of conduction, radiation, and convection. All 3 of those play different roles in a building and in a system. They're all very important, and so we try to find ways to conserve and restrict and manipulate heat transfer through those 3 means in the system. Page 33 discusses the temperature difference being the driving force for heat transfer. Heat always flows from the hot point to the cold point. Whether it's in the wintertime or the summertime, that's just a basic principle that's involved. A lot of times you think about, you feel the cold coming up out of the floor in the building, or you feel a cold wall coming into you. Well, really, what's happening is the opposite. Your body is radiating to the cold space, and you feel the cold, but the heat is flowing away from the body. Page 34 talks about thermodynamics, and I will just briefly touch on that. The first law of thermodynamics says that you don't get something for nothing. Regardless of what the little arrows on the drawing say, a wall cannot release more heat into a room than it receives from the sun. You do not get something for nothing. I think that's important to remember in every area of this project. Second law says you can never go back. Heat always flows from the high temperature to the low temperature. So in working with those 2 laws as fundamentals to this energy conservation theory, we'll keep those in mind. If you can, second law of thermodynamics, if you can conserve the use, it's better to save it going in than it would be to try and conserve it, say through a secondary use as a wall insulation. Heating degree day, page 35. This is a discussion, and I won't get into that very deeply, but heating degree day was developed as a way to allow engineers to estimate energy use in a given building. It uses a 65-degree base, and then that base is adjusted. I'll just read you the definition. The heating degree day is used to describe the severity of the heating season in a particular locale. The higher the number of heating degree days, the colder the locale. The equation that number goes into allows you to estimate your energy usage for your building for a given year according to average weather data for your area. Tulsa, Oklahoma isn't listed on here, but we have 3860. Oklahoma City shows 3725, so that would indicate Tulsa has, according to those numbers, just a little bit different average heating degree day than Oklahoma City. You can see the difference between Baltimore, Maryland, for example, versus Charleston, South Carolina, just up and down the East Coast. Those are numbers that, when you find your number for your area, and we have published degree day data for most cities in Oklahoma, you can use that to calculate your heating loss. Cooling degree day on page 36 is a similar concept, but it's talking about the number of degrees off of a base of 65 for a cooling calculation, and how much energy are you using in your building for cooling. This number is less frequently used because of the cooling process is so much more complex than the heating process. It's used as an estimating tool. In most cases today, we go one step beyond that after we determine what typically the savings would be, then we try and use a little more precise estimating methods than cooling degree days, but it's still an indicator to show in your particular location how you compare, and it gives you a rough tool to calculate cooling energy usage. I believe the information in here lists the Oklahoma City has little black dots on the back of this chart, and Tulsa's on the front, that being heating degree days.
Yeah, that might just note on that particular chart, because it's kind of buzzed from all the copies. What that stands for, HS is a horizontal surface, and VS is a vertical surface, TA is for an angular surface, and then the D and the degrees is degree days at those temperatures. For that particular chart. Which is what Ed said, if you look on the first page on Tulsa, Oklahoma, the total for the year is 3680, and that's based on the degree day 65 as the base. And that's what that chart says, but if you manipulate that and you reference 60 degrees versus 70 degrees, you can see the impact in terms of heating days that you have, or degree days that you have, off of that temperature setting. And that's what that chart's for, just a reference.
What was TA again?
That's for an angle, surface. And where this comes into impacts, if you're looking at, for example, glazing on a building, skylights, the impact skylights have on a horizontal surface versus a vertical surface for glazing versus sloped glass, and then your degree days. So.
I'd like to mention, in just referring to the next few pages here, these are important subjects. Absorptance, reflectance, and transmittance have to do with characteristics of glazing. Many times these numbers are condensed to a factor in a table that you can look up, but in an existing building, you will try to estimate what you have based on what you know about the glass. And many times it's hard to know exactly what your absorptance, reflectance, and transmittance data are. We generally would look at a piece of glass and just judge from experience that it was a brown glazed or a solar gray glazed, clear glass, whatever, and then go to a table and find a relatively close approximation of what the glass is. Unless you have some middle data that you can give to us, that's really the only procedure we have. But as the diagram shows here, the smaller amount of energy transmitted into the space through the glass. In the summertime, of course, the smaller amount of energy comes in. That means the air conditioning load is less. If you can turn that around in the wintertime, you may want to have more coming in. In your case, in an existing building, you're going to just try to report to us what's there as best you can to tell us if this glass is clear or if it's glazed, smoked, bronzed, whatever the condition is, and then we will try and, with your help, determine what those values are. It enters into our calculation as total tonnage in the building, heating and cooling. Altitude and azimuth angle refer to the position of the building and the surfaces of the glass relative to the sun. That is interesting with respect to designing. If you ever get into a situation where you're studying how to position glass in a building, you like to look at how you can optimize the amount of energy received from the sun, or conversely, in summertime, how you can reduce the energy. There are optimum positions for glazing based on the way the building is used in ventilation. I might let Mike discuss that a little bit later, but in our situation, most likely of this study, we will only be dealing with your existing conditions. Relative humidity plays an important role in human comfort. It certainly plays a role in energy usage. It takes energy to raise the humidity level in the wintertime, and it takes energy to lower the humidity level in the summertime. This is an area where many times you let it run wild for energy conservation reasons. However, you want to control it. In certain types of buildings, you are adding humidity perhaps for other reasons. You want to keep that in tight control, or you will have increased energy usage. The high humidity causes certain problems in buildings when, a good example perhaps is the building in Muskogee that's recently been abandoned and renovated because of moisture problems. High humidity allows mold and mildew and other odors and things to develop. So you have to control energy, but you want to control it in an intelligent manner. I should say humidity. You have to control the humidity in an intelligent manner to not overload your energy usage. We typically, in an office building as you would be having, you would probably have 20 to 50 to 60% in the wintertime and probably 50 to 65% in the summertime if you just did nothing. Certain of your buildings, Enid had an area that was a computer center that had to have elevated humidity in the wintertime because of their equipment. So you'll run into these areas. This is simply a discussion of what relative humidity is and what it can do for you. The amount of moisture in the air is measured as relative humidity. Relative humidity is the amount of humidity in the air relative to the maximum amount it can hold at a given temperature. We're all familiar with that, I think.
Ed?
Yes, sir.
One thing here, being a promoter of Oklahoma and this sort of thing, one interesting thing when you talk about relative humidity is that Oklahoma actually has more surface area of lakes, and Wisconsin does. And of course, the surface area of water contributes to the humidity in the air. And I always thought that was interesting.
Oh, yes.
Particularly when here in Oklahoma, a lot of times we don't think of, of the effect of the water and this sort of thing on our designs.
I know I lived in California for a number of years in Bakersfield, and that area was quite dry when I moved out there, and it was because they had dammed up the water and it dried up a lot of the water in the valley. And as a result, the old type evaporating cooler that we used to have years ago in Oklahoma, they were real nice there because they keep that temperature down around 70 to 75 degrees in summertime. Well, they decided they wanted to do some irrigation, so they brought in that aqueduct through there, and then they started letting more of that water in and started filling the lakes back up. And now it caused a whole new boom for the heating and cooling people, because now they're putting in air conditioners where they had the old cheap evaporating coolers before.
There are a few applications in Oklahoma in garages and mechanic shops and things where evaporated cooling will satisfy the load. It's really not comfortable, but in homes and offices, because our humidity is so high, those machines just don't really do the job here. I'm going to skip over a number of these things on human comfort. Those, basically, in energy conservation, we push the limits of human comfort. We want to try to make sure that everyone is as comfortable as possible, but I think we would find that we'll be encouraging sweaters and short sleeve shirts as a means of energy conservation, as a result of the procedures of energy conservation. We do need to maintain comfort, but we do need to control the temperatures. We're talking about lowering set points, raising set points, and so people, I have a habit of, I like to wear long sleeve shirts all summer long, and I find that it's a little uncomfortable at 76 degrees in a long sleeve shirt personally. But so we have to deal with those issues of human comfort, and you all will have to determine for yourselves where you land in that regard. But energy conservation is relative to the temperature of the space, and I don't want to try to quote any numbers right now, but 1 degree change can mean a significant amount of energy savings. So you will have to determine where you want the set points to be set and deal with those issues of personnel comfort at your own level. Let's look back at the, are there any questions on any of that so far? We'll go to site and climate considerations next.
Anita brought, I'm Mike Jones, by the way, and I don't have my coat on because I like to be comfortable. So feel free to get uncomfortable or comfortable or informal, however you like to be. I'm going to back up a little bit. Anita brought up some good points that because of the background and the broad spectrum of the type of people we have here on the glossary and go through a little bit. As an architect, I don't operate on the same level as engineers. They're much more precise, much more scientific, and we need, that's what their job is. As an architect, I'm more basic. I mean, I have to be. We cover a more broad spectrum, and we don't worry about necessarily all the details of what we deal with. But I'm going to put some things that come to mind as Ed spoke. I don't want to rob some of his thunder, but whenever he was describing things, I was seeing different pictures, and you all grab mental pictures whenever someone describes something, what goes in your head. So what helps me relate to, for example, like he was talking about the swing in a building, before I get into the definition, the swing in a building, the way I perceive that, the way it helps me understand, and what he was saying is if you have a baseline temperature and you've got a wood frame house, you'll have a swing like this, where in the daytime it'll heat up and the nighttime it'll drop. And where mass plays an important role, if you compare a house and its swing of a temperature, that it may get as high as 95, even in the wintertime, depends on what time of the winter, and it may get as low as, I don't know, 30, say 36. just pulling numbers out of the air there, but if you take a building such as this, where you have a concrete frame building, brick veneer, a lot of internal mass, which is concrete density, it drops those swings. And that's why mass plays an important role in a building. And I'll give you an example for if you have a brick veneer, or let's say a stone building, it's just wood frame. This will be a little section here. There's your vertical wall studs, and you've got stone out here. I won't go into all the sheathing and all the detail, but okay, what that boils down to is it takes a while for that stone to heat up or cool off before it transmits and impacts your interior spaces. And that's in a nutshell. However, and what we'll get into is the way that'll work for you. That mass is working with nature out here, but it's not doing a bit for you in here, except slowing down the swing inside. What'll help you better is to take that mass, and we'll get into that later in terms of design issues on the inside, put your insulation on the outside and whatever treatment you want. And what happens, this controls the inside temperatures much better than this does, because you have that mass working for the interior and it's insulated from the exterior. Once you get this degree of mass at a stable temperature, theoretically stable, it's never constant, but it helps hold the temperature inside a building. For a cave, if you've been in a cave, constant temperatures back to back 55 to 65 degrees versus standing out the mouth. And that's what we're talking about. The mass can work for you. In other words, when you look at a building, it's better off to have a concrete frame versus a cheap steel metal building. They all have their role and importance, and it's usually economics or the type of application. But mass plays a very fundamental, important role. There was one other thing I thought of that I relate to on the same thing comes into play. We'll get into that when we get into the building systems. I'll just wait on that. It has to do with absorption, reflectance, and then altitude and azimuth, but I'll discuss those later. On the glossary, we throw a lot of terms around, and some of this is going to be boring for some of you who are familiar with it, but some of you who are not, it's going to be very beneficial. And I'm not going to read all these, but I'll read the names, but I won't necessarily read all the definitions. Absorption chiller is something we'll uncover later. It's a process absorption, and it's a chiller, which is a machine. And for example, Hitachi's train carrier now, Hitachi was one of the original, well, they had them before them, but one of the most efficient ones on the market was an Hitachi system out of Japan, and it uses gas fired. You'll hear us talk about those later, versus now the new, I think, train. Is it train that's got the agreement with them, or carrier?
York has the
York.
Hitachi. York has Hitachi. Train is Kawasaki, and Kuwait is Sanyo. So all of the major air conditioning people are affiliated with Japanese York people.
And where that comes about, and I'll leave that to engineers to describe the process, because I'll just confuse you and get myself confused, and we'll all be in trouble. But the bottom line behind this is you have the typical centrifugal chillers we've had for years, which is just a machine like similar to what you have outside your house, but it isn't. And it's used electricity. Well, these are, a lot of the new ones are gas fired, and in Oklahoma, if you can produce off gas versus off electricity, there's that delta of raw energy of, in Oklahoma, you produce off gas, you can save, it's much more efficient, because then they take gas and produce electricity with it. Well, there's that delta right there between the production of efficiency that you benefit versus buying electricity, if you understand what I'm saying, or if I confused you. Because the closer you can get to a raw, like for example wood, if you take wood and take it right inside, you benefit directly from it, just like gas, right into heat. And in electricity, we take gas and convert it to electricity and then convert it into, and so you're one step further down the chain. But what they've done, the impact here in Oklahoma, is it's forced a lot of the manufacturers, even nationwide, to come up with gas absorption chillers, because the efficiency is so much better in terms of cost effectiveness, and that's where an absorption chiller comes in. Active systems, that's dealing with, like for example, solar, which we'll touch on, but based on the current market, it's not going to play that important role right now. It will in terms of passive, but not in terms of active. Air changes, that's an expression, that's an important thing. The engineers calculate your building based on code to have so many air changes per hour. For example, and I'll have them correct me because I can be fundamentally correct but technically wrong. If you have a room such as this and it's a volume of air, then 1 air change per hour is the total volume of the air in this room is completely replenished in 1 hour period. Is a complete air change. And so the code requires you to have certain air changes, so viruses, odors, mildews, whatever the case might be, will not stagnate in the facility. Residential buildings, infiltration, which we'll touch on later, you have so many losses in the building in proportion to the volume and the size and the scale, it's not as nearly as important. In a commercial building, you have much more volume inside the space, you know, in relation to the square footage of the walls, so you have to have air changes. It's much more, and you have more complex systems, but that's what air change is. And obviously, the more air changes you have, the more energy it takes to get that building level to stay at a certain temperature. And the more air leakage that you have, just by sloppy construction or whatever the case might be, age of the structure, you have natural air changes that were not designed by the engineer that happen over a period of time. Weather stripping, bad doors, leaky windows, on and on and on and on. Insulation, lack of insulation, the type of exposure you have with the way you set the building. Air conditioning, I'm not going to touch that, everyone knows what air conditioning is. Altitude, ambient, that's just the air temperature in a surrounding space. Amp meter, that's an instrument they use on electricity to check the actual voltage and amperage of things. ASHRAE, some of you may not be familiar with what ASHRAE is. Most engineers are, or technical people. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers.
There's
And
a
it's-
typo right there that flush should be an A.
Right. And that's an organization that they have come up with policies, procedures, calculating methods, a standard rule of thumb. So instead of your engineer making a lot of gross assumptions, and he calculates his building based on, let's just take degree days. Well, I like 80 degrees, and this guy over here likes 70 degrees, and that guy likes 40 degrees, because one's heavy set and one's real thin. Now, ASHRAE has standards that all engineers, practicing licensed engineers, use certain standards to develop and calculate on. So you can grab, if you've got a problem with building, another engineer can grab the information and go to and calculate, and you've got ways to, you know, calculate consistency and design. That's what it's for. As well as helping solve problems as technology changes. This is an association that looks at ongoing. That's what it's for. Azimuth, I'll talk about later. Balancing, this is important in terms of, for example, and everyone's heard of it, but most people don't realize how sensitive it is and how it impacts energy. Because everyone has a building, then they modify the building, they move a little office around over here, and they change the restroom around. Oh yes, we need to have a multi-purpose room, they move a multi-purpose room. And then, well, okay, that's all right, it's still there. Okay, we've got one of the diffusers over here. But you've changed the way the sizes and the scale of the rooms are, and you've left your HVAC alone. It doesn't work well. And then the next season you go, gosh, it just doesn't cool in here like it used to last year. We need to have a man out and look at that. It's because it hadn't been rebalanced. When they balance your system, they take, and there's little dampers and adjustments all through the duct, and they actually balance the entire system from the last diffuser clear back to the air handler of the unit to put out so much volume of air at every level in the building. When you reconfigure the interior, that balancing and those adjustments are all out of kilter. And it'll impact the way the building stays comfortable. It'll impact, God, it's hot in here. I come over and hit the T-stat, God, it just isn't comfortable. I kick it down again, can't figure out why. Well, you're wasting a lot of energy trying to satisfy this room and freezing the secretary down the hallway going, gee, Merry Christmas, what's going on? And that's what happens. So balance is a very fundamental, important part.
I built hospitals for years, and sometimes it would take us a week to 10 days to balance the whole structure.
That's right.
Because if we have massive changes of temperature, wind, and everything, it's a factor to balance it.
That's right. And good engineers will not allow a contractor to step off, and they will not approve the 10% retainage or sign off on his part until they give you the balance reports and all the data of what they've done.
I guarantee it.
A lot of them don't. You know, someone's like, it's all right. But your good quality engineer is required on any project, I don't care what it is. You know, except usually residential. A ballast, that's a device used to light your fluorescents commonly, well, they got on other other lighting, but the one we're going to associate with or relate to most commonly is going to be your fluorescent. There's a lot more energy efficient ballasts in the market that conserves electricity and uses a lot less. And we'll touch on that later, but it's associated with lighting. A ballast goes on a light fixture. Skip base. Base load, that's a reference point. The engineers use the base load. The building has a base load of so many BTU requirement. Baseboard heaters, I think everyone's pretty well familiar with those. A bellows element, I'm not going to get into that, but that's not that discussed that much. A boiler blowdown has to do with procedures of removal, accumulated, maintenance. Boiler capacity is the actual rated BTU of the unit, just like your heater capacity on your furnace at home. The boiler is like your furnace at home. It's a different piece of machine, but it has a BTU rating capacity to provide heat for the building. I'm going to skip on down. Your booster pump, it's a booster if you have water flow and it has additional requirement to boost more flow. Where those will come in is not so much in buildings. We've got booster pumps in buildings for circulation, but mainly where those will impact in terms of energy for us is going to be wastewater treatment and water facilities, because that's going to be the biggest thing we can impact in terms of variable speed pumps that we'll discuss later. British thermal unit, Ed's already discussed that at BTU. Building performance standards, BEPS is an organization that in the 70s, early 70s, they came along and they said, well, if we can just shave 10%, I think, was it 10% or 20%?
Well, it really ranged widely, but basically they were talking about 20%, I think.
Right, trying to save, if they could save nationwide, the goal was 20% shave it off all the buildings, and you would build your standards to higher standards and better quality equipment, the impact the overall energy. Well, that was the BEPS standards that they developed for people to use, what that was about. Building envelope, or the skin of the building, as architects will sometimes call it, is the actual exterior walls, the roof, the windows, everything on the outside structure, just like the envelope. Calorie. It's similar to heat quantity, to raise temperature, a gram of water, 1 degree centigrade. Capillary action, I'm going to skip on down past those. CCF, cubic feet. CFM. CFM will relate to a lot in buildings in terms of cubic feet per minute, and that has to do with air volume, and that goes back to the balance. And they'll balance your units in terms of CFMs. And that's how many cubic feet of air per minute that comes out each one of those registers. And again, that relates to the air changes per hour, and how many BTUs they calculate that you need, or not BTUs, but CFMs they need to provide so much cooling to this room. The room has a volume, and it has a requirement in terms of cooling, and they back into, well, how many CFMs of air at a certain degree temperature I need to provide to that room to satisfy that temperature. And then how do I balance the whole unit? So that's how those come into play. Chillers, we've talked about a little bit before. There's the centrifugal, which is the typical, most common in large central plane equipment, centrifugals. Coefficient of transmission, that's in the fundamentals that's talked on. Coefficient of utilization, we'll get into that. That's dealing with lighting in terms of efficiency ratio of luminaires. How many lumens are emitted by lamps, and we'll discuss that later a little bit more in detail on that when we get into those. Cooling degree days we've talked on. I'm going to skip on over to page 11. Condensate, just so a lot of people don't understand the principles of, like your outside conditioning on a house, and there's 3 things there. Like condensate, you'll notice that they drip, they get moisture and they drip. That has to do with the process that you get from a heat exchanger, from compression, from heating the liquid, like your Freon, and running it through a expansion chamber, or what I call expansion chamber, coils they call them. And you've got your pressure outside the building, it's compressing the liquid, pushing it into your coils inside the building, then air blows across those coils. And that's where the cool air comes from, and then it's returned back on the suction line back to the unit to complete the loop. But condensate's a byproduct of the process. And a condenser, for example, that's what I was talking about. Your outside, typically a condenser is like your outside unit for residential. That's an air-cooled condensing compressor. Convection, conduction, that's talked about earlier, that's the transfer of heat that Ed's touched on. I might say this one thing on the energy fundamentals, it seems very basic and kind of boring, but honestly, read those and think about them in terms of your own picture and ask questions, because those are the basic principles that everything's based upon from this point forward. And they impact everything that we do and talk about in more detailed information. And they're very important to understand. If you don't understand them, we'll be glad to explain them and relate to them any way we can to you. Because if you just get the picture of that, then you understand where we're trying to go. Cooling load, that has to do with the actual load of the building they design. The building has a total load. Well, this room has a requirement for so many CFMs, that room, they add all the rooms up, and you have a cooling load. That building has to have so much X of energy to produce a load to maintain a temperature, and that's cooling load in generic terms, not in engineering terms. A damper, that goes back to, a lot of times they're used in your gas flues. They're also used in your fireplaces, your dampers. They're also used to balance at your diffusers. They've got little dampers in them. That's what we refer to when we're talking about dampers. Declining block rate, I'll let Charlie discuss that. He'll go into that in detail. That has to do with your utility charges and the way you're charging utility bills. He'll discuss later. Skipping past degree days. Demand charge, again, that's dealing with utilities. Charlie will be talking about that later as well. Demand load, he'll be discussing that as well too, and your demand, your peak demand. All those impact the way you charge electricity in terms of kilowatts. Design condition, design temperatures. Your design temperatures, engineers look at from the standpoint of for example, if you've got a machine shop that produces a lot of heat inside, they use different design temperatures than they do for a library. Different design temperatures for a garage facility, a filling station. Depends on what, if you're going to have the doors open all the time, like to a filling station or a fire station, you don't want to try and maintain 60 degrees year round. It's not going to work. You're going to waste a lot of energy. So they use common sense and make value judgments, and that's what we're going to get into you on, is the way you use your facilities and use common sense, and how you can, just like Eddie touched on, the short sleeve shirt versus the long sleeve shirt. Architects, all professional people wear button-down shirts, long shirts year round. It's kind of stupid, but we do, every one of us. You feel pretty stupid when you're going, God, it's hot here. So you see us all go around with our ties pulled down and pulled apart. Everybody goes, well, that's kind of tacky. Well, yeah, I'm burning up. But getting sidetracked there a little bit for you. But your dew point, that has to do with your relative humidity. When we get into more detail later on in the design issues, I'm sure Ed can delve on that a little bit further. Diffusers, I've talked about them already. Well, those are the little grills right there that provide the air through. That's when we talk about a diffuser, we're typically talking about either return air grill, and I never have figured this out, maybe Ed, in 17 years of practice, why do they call a return air grill a grill and a supply air is a diffuser? One's a return and one's a supply. They do the same thing. Why aren't they all diffusers?
Well, the simple definition is the diffuser, of course, throws the air out.
Diffuses it.
That's a diffuser, a technical term, but they really distinguish. There's a grill and a register. A register is one without directional dampers, and the grill has directional dampers. That should be called a return grill, but it's really a return register.
Okay. See, now there's the difference between architect and engineer. I understand all that, I've known it for years, but they're both grills as far as I'm concerned, but they aren't. In reality, they aren't.
We call them supply diffusers and return grills, and we mix up the words all the time, but we know what we're talking about.
Okay. Direct radiation on page 13. That's dealing with solar, and where I want to talk on that is not solar in terms of solar collectors, but your building is a solar collector. And passive solar is dead, they say. Well, no, passive solar is common sense. It's working with nature, and we'll, without you knowing, unless we tell you, we'll be dealing with passive solar throughout the entire project. Example, direct radiation is the impact of glass. It'll radiate heat. It absorbs heat, radiates heat. It is a direct receiver of radiation from the sun. Your brick and everything else is too, but it doesn't transmit it as fast. Where glass is a collector, it will receive it faster and process it faster into a building because it has no mass, and plus it's transparent. Things travel through. So that's where direct radiation comes in. It's directly from the sun, casting on everything. Discounted payback, I'm gonna pass those. Domestic hot water system, well, I'm pretty well familiar with that. Dealing with domestic, that means drinking water, washing water. It's your door seals, another word for weather stripping, used for overhead doors or roll-up doors or different types of doors, or your garage doors. There's a bottom door seal on the bottom of it. Double glazed. You want to distinguish between double glazed versus thermal pane. A lot of houses actually have storm windows added on to the regular or single glazed windows or a single pane of glass. And then you have double pane or thermal pane. What I prefer is there's two panes of glass with a divider hermetically sealed. They pull a vacuum on it and they put a drying agent into it so no condensation gets between. And the way you can tell when they're bad is if you have moisture build between the two panes, the unit's bad. It doesn't have the insulating value it once had. And it still insulates better than a single pane, but it doesn't insulate near the quality of when it's sealed with no moisture between. Dry bulb temperature, that's again, I'll let Ed deal with that later on. That's dealing with your humidity, your dry bulb, and your temperature range. Dual duct system. I don't know if we want to discuss on that at this point or not. I'm going to go this way just on duct work at this time. You've got duct work, and what they're referring to is the sheet metal or the material used to get the air from the air handler or the equipment, for example, in your house, from the furnace and the blower where it blows the air through metal ductwork. It's just a tunnel that the air flows through to the grills, and it's just, that's where it comes from. Economizer cycle, now this is an important one that a lot of buildings do not have that they really should have. It's a free cooling opportunity. For example, like this building, it wouldn't surprise me if it does not have. The economizer cycle is you have air changes, back to the air changes per hour, or what they call makeup air. You're required by code to have so much makeup air in a commercial building to make up with fresh outside air to supplement the air that you're returning and bringing back in, which also deals with the air changes per hour. Well, then there's an economizer cycle that you get free cooling in the wintertime. Instead of producing from refrigeration equipment to get coolness to the air handler to provide cool air, you can just take outside air. I mean, when it's 30 degrees outside, there's no reason why you can't draw air directly from the exterior temperature right into your system and use that air to cool the building. A lot of buildings do not have that capacity. The city hall or city administration building in the city of Enid uses refrigeration year-round. They have a cooling load year-round. Most of your commercial buildings, this one does, will have cooling load requirements year-round. Even if it's 15 degrees, you'll have parts of the building that needs to be cooled. And they produce it with refrigeration. Well, it wastes a lot of energy. When it's 15 degrees outside, you think, God, open the door. I mean, common sense. Well, the economizer cycle comes into play, but then you get into other issues that Ed will deal in better. Is that's not always best. You need to have more than that. It depends on what the humidity levels are, because you know if it's 15 degrees outside in Oklahoma, it can be extremely dry, and the way you feel warmth and comfortable in the winter is humidity level and your temperature. So if you take dry air out there at 15 degrees and you've got a cooling load, that's going to mix with the rest of the building, and now to satisfy your heat areas, you just cause problems in your control systems. So they've come up with solutions to that. Again, engineers have come up with ASHRAE, they've developed standards, and they've come up with new pieces of equipment, new control systems, and how you can deal with that and still get the economizer cycle. And we'll get into those later. I'm going to skip on over to page 15. See if there's anything else. Evaporative cooling we pretty well touched on. A lot of these, a foot candle, just tell you what that is. A lot of times we'll show up with a little meter, hold it up in the air and punch a button. And a foot candle is just deals with lighting or luminaires. Your lights give off so many levels of luminaires or so many foot candles of light. It's just a element of measure. just a unit of measure is all it boils down to. That there's different standards set up by IES, which is the Illumination Engineer Society, which says a conference room should have lighting levels of so many foot candles versus an office of drafting should have, say, 200-foot candles. A general office should have 100-foot candles, half the light. If you're in a library reading, it's less. If you're in hallways, you can get as low as 40-foot candles. And the reason I'm touching on this area is what we've uncovered is everything from 400-foot candles to 15-foot candles. Some workspaces that really need light, and other workspaces are way overlit. And City of Enid, and it all comes down to energy, and that's where you'll see in lighting later. You want to use good practice, and you want to provide adequate light, but since overkill, and even in this room, there's overkill right now. For what we're doing, there's no reason to have those lights on except for the cameraman to see my ugly face up here. You can see your task right there. You got the fluorescence, and you can see me, and I can discuss with you, and everyone can see your task. But yet we have these lights just to have them. So that's what we're dealing with. Is we don't really need those for this function. But yet every day when you walk in your building, you go on, get all the switches. Yep, okay, we go, and you pay for it. So you need to use good common sense when you with design. We'll talk about that later. For your foot candle, it all goes back to how many foot candle levels we're dealing with to satisfy the task or the function to accomplish your work. Glazing is a term. Well, let's back up to glare. Glare is an important element with lighting as well. And it's a sensation. You get them off your glasses, you get them off. If you're around the building, everyone says, well, use natural light. We can use natural light to solve the lighting, turn off all the lights. That works on the north side in the wintertime, and it works on the north side in the summertime if it's not early morning, late evening. Because that's where the solar comes back into play on a building. I'm trying to relate a lot of this together. For example, and I'll touch on this a little bit more. If your building sets here in Oklahoma in the wintertime, it gets your peak is December 21st. It gets about 37 degrees, and the track of the sun is like this. In the summertime, the track of the sun is like this being north. So in the early morning, if this is to the late evening, it'll get in the north glass and it'll provide glare. That sunlight, you want to save, but glare will impact the performance of work. If you're sitting there and you can't see, or you've been behind a car going down the highway and a bumper hits and just blinds you. Well, it's not quite that bad in buildings, but the way you offset that, you have to provide more light on a perimeter to offset that glare consideration. To kill, and actually you overpower is what you're doing. The light coming in, you're overpowering it to knock down that glare. Well, it's kind of stupid. If you design your building, which we'll talk about later, if you design the building to consider all these factors, then you can use natural lighting, understand when you can use it, how you can use it, and the limitations of it, and you can save energy instead of overkilling to compensate. We have historically in America, through technology, ignore fundamental principles of common sense in this 20th century, and we can solve our problems through technology, and you can to a point if you're willing to pay for it. Glazing, that's a term for glass. That's all it boils down to. Instead of having a window that has glass in it, if you have like all this glass we have out in front, that's called glazing. Don't ask me why, but that's what they do. Architects do that too, just like engineers on their grills and diffusers. Gross wall area, I'm going to pass by those. Heat exchanger, that's important, and this is where I'll probably get in trouble describing this to you, but there's heat exchangers in everything we do. And it's in processing of heating and cooling, processing of food, processing of chemicals, processing, and they basically give off, they exchange heat. For example, your coils in your residential house, or your coils in your air handler or your coils in your car on your radiator, that's a heat exchanger. Basically, it's an element that absorbs and transmits and cools a liquid or air. In other words, you'll have the radiator has hot air or hot water returning from your engine on your car. It has to hit the radiator. The cool air driving on the highway blows across it, drops the temperature down, and picks it back up and takes it back in the engine. Same principle is used in refrigeration all over the world. I mean, it's that basic in terms of but it's a lot more technical in terms of how you make it work, but that's the theory of it. It's a heat exchanger, and they're in everything. Oil field equipment, and it takes energy to process heat exchangers. It takes energy in that car, you burn gas. So basically, in essence, that's what a heat exchanger is in non-technical terms. Your heat gain, that's used typically, you can read that right there, it has to do with anything gain internal or external on the building load. The more you have heat gain in the summertime, the more you're going to burn energy to cool it. From lighting, from people, from your solar load, from any machines and equipment, computers. Computers is one of the largest impacts that we've had. Lighting is the biggest impact, one of the major contributors you'll see later in the seminars to your interior load. And then your second one that's hit this last 2 decades is computers, PCs, and other process equipment inside that is used. It has a major impact on how much energy you utilize. Heat loss and heat load. Again, the heating load's a load on the building and the elements of the building. The heat loss is how many degrees you lose. And that's, again, back to that's what I was talking about outside of air changes, your heat loss, and that's dealing with the quality of construction, your weather strippings, how much you produce so much energy inside a building, or how much do you lose per hour. Well, if it's a brand new building, they have a less loss rate than a building that's old. The older the structure gets, it's a function of maintenance, also a function of when it was built and the technology and the materials when it was assembled. Impacts your heat loss and your heat gain, because the only difference basically in terms of external, if you have a wall, here's your inside space, here's your happy people, they're so comfortable. Your heat loss is, you've got this 75 degrees and this is 25, is how much in terms of BTUs transmit to the exterior on an hourly basis. And your heat gain is how much from an external standpoint, not talking about internal heat gains, is how much you gain on an hourly basis. It'd be nice if you gain the same amount that you lost, but it never works that way. Heat pumps, we've all talked about heat pumps, or heard about heat pumps, what they are. You have utility companies that really promote heat pumps process. Without going into more detail at this point, we'll discuss that in refrigeration and things later. And Charlie, I know what he's thinking back there. No, I'm not going to say anything at this point on that. HID lamps, high intensity discharge lamps, basically they're just higher quality, less energy consumption than typical fluorescent or incandescent. Metal halide, high pressure sodium, low pressure sodium, quartz. However, I don't consider quartz a very good quality of, they really consume energy bad. But your HID lamps, and there's all types that are available now that really put out good quality of light. And they have a higher efficiency range typically than fluorescent and incandescent. I'm going to rob just one piece of Charlie's thunder on lighting, because it just is phenomenal to me. And for an incandescent that everyone has in their house and everything, only 10% of the energy utilized is given off in light. 90% of all the electricity that goes in that bulb, in the filament, is wasted, is given off as heat, as a byproduct. Only 10% of electricity consumed is light. You have the bulb for light. I mean, that's phenomenal, 90% waste. Okay, on fluorescence, it's about 30%. About 30% of all electricity used. Okay, so you got 70% of both, well, 90% in one case in this room of all these bulbs adding to the air conditioning load right now as we're sitting here, and 70% of all the electricity consumed in the fluorescence given off to the building. Seems pretty wasteful. So you can see them, and the reason I bring that up is dealing with, we're talking about HID lamps and efficiency. You can see why it's very important. Back to what I said earlier, foot candles don't overkill. Why provide all this surplus light? Because all you're doing is giving off a byproduct that you have to refrigerate or heat. Well, in the wintertime, it's fine. It's, again, but there's more efficient ways to heat your building besides using light bulbs. And that's fine if you're going to raise little chickens and you're going to put a light bulb out there with them, but when you've got a lot of people, it's not a very efficient process. Infiltration, we're gonna talk about that a little bit. I don't think we even discuss it right now. Infiltration, we're gonna discuss later, and it's important in terms of building envelope, and I'll deal with that in more detail. Kilowatts per hour, Charlie's gonna touch on that, and that deals with, your kilowatts, how many thousand watts of electricity used in a 1 hour period. And there's kilovolt and Langley, and I'm gonna get past those. Life cycle costing, basically, we're gonna talk about that later in the process throughout the program. And life cycle costing deals with, and we're trying to get everyone to think in these terms because, as Charlie showed you in fluorescent lighting, first time cost is not where it's at. You can buy a bulb for half the price is not the thing to do. Because your half price bulbs, they've got you, you've seen the Fram oil filter, pay me now, pay me later. Well, they get you coming and going. You can pay me now and you're gonna pay me later. But on the, excuse me, I lost my train of thought. On life cycle costing, what we're dealing with is the initial cost, the cost to maintain, the cost to operate, electricity, et cetera, and the cost to replace. It's the whole life cycle, the whole cycle of that one product, from conception to end to replacement. And that's what that deals with. Load profile, that's something that Ed will have to deal on better. There's a load factor, deals with the actual calculation. There's a load profile. Every building has different load profiles, and it's a plotted graph with the characteristic of the building. For example, it's highly unlikely, but you may have a building instead of having a typical swing like this, that may have a swing like, and it starts dropping faster, and it may come back and go back down. And what I'm thinking of is depends on if this is a daytime, you've got an internal process, they leave at 3:30 in the afternoon, like manufacturing, and then temperature drops back down, and then about 8:30 or night shift comes on, they start producing internal equipment again. There's load characteristics of a building, load profiles and load characteristics, and every building's different. And so that's what they're dealing with there. Lumen we've talked about, luminaires we've talked about, makeup air I've touched on, multi-zone unit. I'll cover all those at one time just so you can understand. A single zone versus a multi-zone. A single zone is you have one air handler or a house is a typical single zone unit, unless you have two units. An upstairs, downstairs unit on a house is a multi-zone unit. You have an upstairs unit, downstairs unit. You have two zones, upstairs and downstairs. Commercial buildings, you have several zones, unless it's a very economical system. And what that is, you'll have a thermostat for every zone. On this case, it's a sensor, which goes back to a control system. But every zone will have an air handler, a set of ductwork, return air grill to it, and a thermostat, and that's one zone. And depending on how many zones you have, depends on the complexity of the system, and depends on the utilization within the building. Hospital is one of the most complex you can ever get into, besides clean air facilities, clean air rooms. A plenum, another term used a lot that a lot of people don't understand what that is. To save on the cost, you have all the ductwork costs to provide the air to get to the space, to run all this ductwork. Well, there's a space between the ceiling and the structure, and it's usually 2 to 4 feet, typically in a range. That's for this cavity that they run all your electricity, your lights, your wiring, your control systems, your communication wires for your phone networking, everything. And that's where your ductwork will run, in that little cavity space. Well, all this cost to run the sheet metal or supply, well, what they'll typically do is they'll use a plenum for return. They'll just stick a grill in the ceiling in several rooms, and then have a grill way back at the wall. On the other side of this room, for example, if this was the air handler room where the equipment was at, we just have a big grill right here. And let the air from this room return directly instead of having ductwork in the ceiling, pick it up, take it through the plenum and back. Well, that plenum, if they use for plenum return, has different requirements of what you have to do. But that's typically what's done now, because the economics is return air plenums, they call them. Well, that plenum is just that cavity of space, is what that is. Feel free to have any questions or see anything that that you have a question on. Pneumatic versus I might touch on that. Pneumatics on control systems. you have typical electronic or pneumatic, and pneumatic are your older. Pneumatic is a little compressed air, and you have valves just like, and this isn't the way it is, but the way I relate to it, you little air compressors you have on your aquariums at home, the little wire, you know, little tube, well, that's kind of what they have for buildings, and it puts a pulse of air or a vacuum, and it actuates dampers that we've talked on earlier, and they can control if you're bringing cool air into a room, say this room for example, they'll have a damper that will control how much air comes in this room, and if it satisfies temperature, the T-set says, I'm satisfied, then that pneumatic control goes zzz and closes off the air volume that comes into the room, and then when it says I need more air, zzz, it opens back up. Well, there's electronic and there's pneumatic, and the new systems are typically electronic. They're much more temperature sensitive, controlled computers, but then there's a lot of pluses to pneumatics, and I'm going to let Ed and them discuss that at HVAC, the pros and cons of different systems and why. On page 21, I hope I'm not boring everyone to death with some of these, but I'm trying to relate to why the importance of why these are in here, even though they're so rudimentary and basic. But the reason why Anita brought this up, architects and engineers take a lot of things for granted, and it's so frustrating, and she brought it home to me, is you go talk to an attorney or a doctor, and they're so used to their buzzwords, they lay this out on, you understand? We don't look like a fool. You say, yeah. You leave and talk about, what's he talking about? Was he talking about this end, or was he talking about this end? I don't know, man. And the same way with your attorney, well, I'm gonna get sued over this. You want to understand, but you don't want to look stupid. And so we're so used to using these terms, we just take for granted everyone knows what we're talking about. And you don't. And it's not a matter of looking stupid. It's a matter of, you've got terms that you use in your line of work that I don't understand. Accountants, I've got terms that you don't understand. So we're just trying to go through some of these so you can pick up on what we're talking about and understand our buzzwords, so to speak. Reflectance, that's the reflectance. Where that comes into play on page 21, reflectance is, for example, it deals with the radiation coming into the building, how much is reflected off the structure, off your glass. There's a certain percentage of light that's reflected or heat that's reflected. It's also true inside a building when you design a building for lighting. That's where the foot candles and all that comes in. Is a surface has a certain, well, it's the same principles, back to those principles of when light is cast on this, of a white surface versus a dark surface, there's a certain amount of absorption that this will literally absorbs light. I mean, it physically doesn't, but it does in the essence of how much light's given off to a room. And if you paint the room dark black with the same lights, it's a lot darker here versus white, and that's basically it in a nutshell. And that impacts how much energy you use, how much is reflected into the room, how much do you see. And it's the same true on the outside of the building coming in, how much is absorbed, how much is reflected, how much is received, as it is inside a room with light and heat. Every material, every color has absorption, reflectance, and how much it gives off, how much it receives. Okay, I'm going to skip on over to page 23. I probably touched on all these others in different ways. Ed's talked about your R factor and your R value and seasonal efficiency. If you look on your new equipment, especially on residential, well, in fact, it's on everything. ASHRAE has required, and it's now passed laws, there's certain efficiency level ratings that all equipment has to meet. And I don't know if it's forecast over a 5 or 10 year period, but for example, your residential grade exterior condensing unit by the year 92, I believe, has to be a 9.0 efficiency rating. Where just 5 years ago they had them 6.5. And what that, and I'll have Ed make this technically because it'll be better for you. The rating is how much energy it can produce with how much it takes to produce. And I'll let you on your EERs and SEERs.
The seasonal efficiency is discussed in here, but basically it's BTUs per watt. Is what EER is talking about and what SEER is talking about. BTUs per watt, that means the cooling generated divided by the amount of wattage it takes to do that. And so, no 6 versus a number that would be a 9. It would, a 9 would generate 9 BTUs per watt of electricity. Is 50% better than a 6. And that's simple, simply just a rating number to compare
Right.
one that's good versus one that's better versus the best.
Right. And as we'll touch on later, the importance of, and that's where we get into the money saved. Every city has capital improvements, capital improvement committees, and or a fund for improvements. Well, what we'd like to see you do, instead of using the total dollars of savings to buy equipment, use your capital improvements, but then use this fund to augment for higher quality of equipment. Because if you buy, for example, next year, 9 SEER rated equipment, that's a bad investment. You're buying the bottom line. That's like buying a Cadillac with a 454 right now instead of a V6 with the, electronic fuel injection. You're buying the worst end that just barely gets in the market. Example, Mercedes-Benz. I mean, they're highly thought of, highly touted. They're good cars, very fine engineered cars. But they pay in America millions of dollars annually in a penalty clause because they cannot meet EPA requirements of fuel economy. Once more, they really don't care. They're a luxury automobile. If you can afford these, you can afford the gas.
They're just passing the cost on, basically.
That's right. And so you're doing the same thing to yourself without realizing it when you buy equipment that meets bottom line standards. And 9 is the new standard in residential grade equipment. So what you want to do is buy the best that you can technically afford at that given time, because in 5 years there's going to be better equipment. In 2 years that'll no longer be the state of the art, the best equipment. And I'm not talking about being on the cutting edge of buying risky, well, let's go buy an Edsel, because man, this is where it's at this year. No, we're talking mainline products, but buy the best quality of those products that you can afford, because there's going to be more efficient equipment later on.
That's going to depend on the quality of the equipment plus the savings. You can have a poor piece of equipment that saves you a lot of money.
True.
But if you're replacing that thing about every 3 years, it's not worth it.
Right. And conversely, the same is true as well, as if you've got short life equipment, you may not want to buy the most expensive, highest piece of equipment, because you might calculate, we've run across this before, you might calculate and find out that instead of a 9, then there's a 15. Well, the cost of 15 today is so much money, it's cost prohibitive. You're better off get 10 to 11. And then in 5 to 10 years, 15 years when we replace that, the 15 now is the bottom line, and now you can, so you don't necessarily want to go from the lowest to the highest quality in the market, because you pay such an extreme penalty to be the best. If everyone's the best, in suits or anything, you pay a penalty just like if you're the worst. So we don't really promote that. That's a good point. You have to calculate and look at it, and look at your actual savings, your payback, and the life cycle cost of what you're talking about. Get into those. Going over to page 24. U value, the only thing I'm going to say on U value is it's the inverse of the R value. And I'll let Ed clarify that in terms of how R and U.
Why don't you point out a typo under ton of refrigeration? Again, that's 12,000 instead of 12.
Yes, there should be a comma.
Where?
On page 24, a ton of refrigeration. That's a good point. We ought to talk on that anyway. 1 ton is equivalent to 12,000 BTUs. Again, I relate to residential because it's the easiest for everyone to relate to. If you'll go back and look at your equipment, for example, on the outside of your house, there's a little nameplate, and it'll have a SEER on that, or a sticker. It'll also have your tonnage rating, and it'll be expressed in BTUs. 12,000, 24,000, 36,000, 48,000, 48,000 to 4 ton, 60,000, 5 ton. And they rate the tonnage in BTUs, and that's where that comes in. The same is done with commercial equipment, but you don't go around and find an SEER or a tag that tells you. I mean, there's tags on there, but a lot of equipment doesn't have it on there.
A lot of the older equipment has tags, but they didn't start coding the nameplate numbers with corresponding BTU values until very recently. And in some cases, they still don't.
Right.
So the important thing there would be to get the model number and the serial number, just so that we can trace it down if we have to.
Right. Because we've went out, for example, on units, and I mean, they've been sitting on the roof, and you can't even tell what they are. They've been for so long, and there's no maintenance on them, and so it's volumetric. Look at the motor, yep, about 3 ton. And that's as accurate as you can get. There's no model number left on them. You can tell they're a carrier or a train, but based on experience, you can get pretty close. I mean, you can get within a half a ton. Typically, they come in certain sizes and scales, and there's ways to tell.
I remember some of the old units rated about 90,000. Today, that 9,000 is a little box about like this, you know.
Mhm.
And that thing was larger than those that run 3 ton now, you know. It's
That's
around
right.
90,000.
That's right. Those are refrigeration things. Vapor barrier, that's an important thing on, it deals with the building envelope. It also deals with many other things, but typically the way we relate to it is that for years they put them under the slab for a vapor barrier so the moisture wouldn't get from the ground through the floor slab into a house or commercial building, depending on the application. But also the same is true on the exterior wall skin or the envelope. We use them a lot now as not for vapor, it works for that, but for infiltration. The same theory behind it works very well for infiltration, to cut in infiltration losses through a wall. And you've heard the term visclean. Lots of trade names. It's really not visclean. Everyone calls it visclean, like sheetrock. But technically, that's not the proper term. It's a polyethylene something. I can't think of the sheet of polyethylene plastic material, but everyone calls it visclean. And there's different qualities that you can buy, different mill grades and thicknesses. Variable air volume, the last page. Well, no, I'll skip 2 pages. No, I didn't. Last page, variable air volume. That's a more complex. You've got a single zone, a multi-zone air conditioning system, and you have a variable air volume system. And basically, well, I don't know how to describe it without getting technical. You have zones within zones. You have an air handler, which is a zone, and then you break that zone into smaller zones. For example, if you have, well, we can take this room. I'll probably Ed describe it a little better.
Yeah, let me just say this about variable air volume. The system was designed to track the heating and cooling load by varying the amount of air that's delivered to the space. The air carries the cooling or the heating. Your heating load is a variable number that goes from no heating required all the way to maximum heating required. And the same thing on cooling. Variable air volume system simply tracks the heating or the cooling requirement with a variable amount of air, so it provides just enough air to meet the cooling or the heating requirement. And the thermostat distinguishes at what point it switches over from heating to cooling. The control system does that through the thermostat. As opposed to the other method, which is to deliver a constant supply of air and vary the temperature, which through that UA delta T formula that we use, or the NDOT CCP delta T, you can vary the temperature to get a Q, or you can vary the volume to get a Q. So variable volume is the one method versus variable temperature. Those are the 2 basic ways to deliver energy into space. There's quite a bit more to it to discuss, and we can discuss later, but that's essentially what that is.
Did everyone grasp part of that? Because it takes a while. I mean, he put it in a nutshell, but yet, unless you're familiar with it, I know exactly what he's talking about because I've done variable air volumes on projects.
Well, later on, I think we can diagram that
Right.
on the board and show the different systems and how fundamentally they work,
Right.
to help you recognize what you're looking at when you go on.
Right. And to relate how that impacts, just backing up a little bit from back to the humidity and the comfort zone and all that, those other charts that Ed touched on. The variable air volume, like you said, the 2 processes, either temperature or air. Well, the temperature can be higher if you have more air blowing across you. In other words, because see, you're in a evaporative system, your body's a heat exchanger as well, and the way you deal with heat is perspiration. And when you perspire, you've all been hot, then all of a sudden a breeze hits you and it's kind of a chill. Well, that's what we're dealing with in a different means, but that's how your body deals with situations. Well, that temperature can be cooler with no breeze, or the temperature can be higher with a breeze, and you have the same comfort level. Well, that's what, variable volume in essence is dealing with the volume of air that you're moving versus the temperature. I mean, not quite that, but see what I'm trying to say? But he'll deal more directly on the actual engineering aspects of what we're talking about. Vestibules are very important. In years gone by, they were called mud rooms. And in fact, in the Northeast and Northwest and different parts of the country, they still have mud rooms. And what they are, they're room to go into, and it's airlocks. Some people call them airlocks. If you're in the Arctic area, things like Alaska, sometimes they're called airlocks. But it's a vestibule. Every time you open the door, you flood the structure with unconditioned air, with whatever the temperature is, whatever the relative humidity is. And the more you open that door, the more you impact the structure, and the way that it has to receive that air to the return air grills, process through running electricity or burning energy to make it acceptable to whatever the conditions are inside. So half the buildings around, or more than half, don't have vestibules, and you're just flooding directly in the building. You can cut that down substantially, the impact on the load of the structure, by having vestibules. It's a buffer space.
That's why you take your overshoes off.
That's right. Well, that's what they used to do, because in the old, they would, in fact, in Scandinavia and Norway and places like that, and this touches on all the principles, in essence, they would have a fireplace. We typically put a fireplace in the outside wall so we can open it back and drag the ashes out and throw them on the ground, or you don't make a mess in the house. Well, in Scandinavia and places like that, they have the huge stone rock fireplaces on the inside of the structure. They use the entire mass because their seasonal heating is all winter. Okay, and once they get that mass solved and they keep that fire stoked up, it keeps the temperatures. It shaves the peak. It does back the peak shaving, what I've talked about. And that's why it's important. What I'm going to tell you is very important with Oklahoma versus others, because in Scandinavia they have a winter load and a summer load, but their summer load isn't anything like ours. And I don't know all the particulars, but in theory, once they get that building satisfying temperature for the heating, they're not going to have major swings. They're going to start dropping those swings down through their mass and their fireplace. What's going to be on the inside of the building. Okay? In our area, in Oklahoma, we do not have constant temperatures in the wintertime of 30 degrees. We can't use that type of application. And this is just the fundamental difference. We don't need a large stone fireplace in the interior of our house, stoke it up, let it run 24 hours for weeks on end, because you'll burn yourself out. The difference we have in Oklahoma is we have 75 degrees today, and tomorrow it's 30. And then it's down to 19 for a week, and it's back up to 50. We have quick loads that last a week or two. Well, a large stone fireplace stoked up and running and it's getting that rock hot and it's sitting there all winter long will kill you. You'll be opening up your windows half the week. What works better for Oklahoma is a wood stove. A direct load's put on, you put heat in it, it gives off immediately. It starts satisfying the load put on it. So I'm getting a feel of what I was talking on there a little bit, but that's the difference in different countries, different cultures, different environmental loads, and that's the vestibule. That's what I was talking about. Got off on the fireplace there, but the vestibule is the same thing. That's where they come from, because they have a constant load all the time. They go in there and they're having to take off all their coats and all their boots and all their galoshes, and then from that room they go into the regular house. I mean, it works really well in those cold environments. Well, it does the same thing when you have a vestibule here. It knocks off that. But, weather stripping, I'll touch on that a little bit later because it is phenomenal, the difference that weather stripping can make. Obviously, no one believes weather stripping makes a difference in a building, because all you got to do is go around and look at all the facilities. You go to my house, I know it makes a difference, and I've got some bad weather stripping. My house is 6 years old, and there's a couple of doors that have a leakage, and every winter when I got a draft come in there, I say, I need to have them out and get that replaced. And I've been in the house 6 years. And I need to change it, and I've not changed it. So I'm convinced that no one truly believes the impact weather stripping has, because it's amazing how many facilities have terrible weather stripping. It's such a simple thing. It's such a small thing. It's just a little crack. I mean, it's just a little crack. How can it really impact? Well, this afternoon you'll see how much it can impact the load and back with your heat loss, heat gain. It's amazing what it can do. I think it's all I'm gonna touch on definitions. I probably put everybody to sleep already.
One thing, Mike, on the wet bulb temperature, that's the next to last definition. Of course, we use wet bulb and dry bulb temperatures in the design of our irrigation loads. And going back, while I go to the comment I made about the surface area of water in Oklahoma, these data are established by ASHRAE, which is, the old conservative type organization. And a few years ago, I guess about 15 years ago, ASHRAE raised the wet bulb design temperature for Tulsa 1 degree. And that created all sorts of articles in journals and everything, because they don't normally do that. But again, that just points out what Ed had alluded to earlier about relative humidity and moisture and this sort of thing. So we do have, in Oklahoma, we do have a lot of moisture.
That's right. And where that comes in, to a good point, the fact that, and I'm sure we'll discuss a little bit more, is the wet bulb, your comfort level, or your perceived comfort. Everyone perceives comfort at a different range, but the accepted norm, it depends on the relative humidity, the wet bulb, then there's the dry bulb, and you've got the entire formula, and there's a certain point where they all meet if you graph them. That is a comfort zone or comfort range, and that's what those little bitty, at the back of the last part of energy fundamentals. In rudimentary terms, that's discussed under bioclimatic chart, and the comfort, you show the little figures on there, where there's a range that's acceptable. And it all depends on more volume of air, lower temperature, or the humidity level at that elevation. So there's several ways you can vary that, but it has to be, you have to stay in that zone of comfort, and the way you deal with it depends on your exact condition and what the problems you have. I'm going to back up one step further. We skipped over under project overview. I'm not going to read all these, but these little graphic illustrations, it's behind the little blue separator. There's page 2 on how to save energy dollars. I mean, again, this is like the definitions in the energy fundamentals. It's so basic and boring to a degree, but yet it's exactly tells you what we're going to do in the whole process of the program. For example, this is seminar 1. There will be a second seminar. This one, what we're trying to do in the next 2 days is gear you up to understand why we're doing what we're doing, why you'll be doing what you're doing, the principles behind what we're doing, the theory behind it in relatively terms, and to direct you towards auditing, to direct you towards the task of collecting all the data and understanding why you're collecting all the data and the importance of the data, because the bottom line is garbage in, garbage out. It's like a computer. The more accurate the information, the more precise we can be, the more accurate that we can be on forecasting savings, the more accurate we can be on the next phase of design. And that's the second seminar. This one's more basic, but we're tasking you towards this very specific, very, very important task of collecting the data and why you're doing it. And in the next seminar, once we have all the cities with the data collected, we're going to have a seminar on the design and the principles of the design and the more direct, involved application of all the theory, of the basics that we've learned at this time. How we take all the garbage and do something with it. But on page 2, the next few pages, these just basically go through, and this is what this first seminar is about, is we're going to go through the handbook, item 1, understand it. Now, number 2, we're going to look at your utility bills and find out what you spent last year. That's what starts the baseline data, is a reference point of every facility and what they expended. Then we'll perform an audit on the building, item 3, you know, and going through and collecting all the information. Item 4, it's not gonna be as important, but where I differ on asking employees for ideas is more how they utilize it. Your building maintenance people, how they operate in the buildings, how are the people that are using the buildings, how are they operating? I mean, it's important, is that a controllable lock thermostat? This one is a sensor, you can't do anything to it. If that somebody come out and adjust it. But on a thermostat, is it someone who just comes in and says, well, it's hot in here? I went to one facility in Oklahoma City, and it was in the summer. No, it wasn't, it was in October, and it was kind of cool outside. It wasn't cold, it was probably 60 degrees, 65 degrees. And he had a window unit, and I was freezing. He had a short sleeve shirt on and tie, and that window unit, I was literally freezing in the man's office in Oklahoma City. And are they operating the building that way? I mean, he might be comfortable, but there's a certain acceptance level that you have and accountability. You want to pay for that man's comfort to that degree. And that's true with the entire building. That's a value judgment you have to pay. If he's a city manager or the mayor, you're probably willing to pay it. If he's not, you're probably not. But, you know, that's a value judgment you have to make on how you operate your building. But you need to ask your employees, you know, if they're just open T-stats, who's controlling them? You know, who sets that point? I mean, in St. Enid, we found in one building, it's a convention or a conference center. And it has several conference rooms, several different for agendas and meetings. It's a large facility. But we found thermostats in summertime, everything, with one of them had the heating on, it set on what, 80 something? In the conference center we used. And then we had another one on, it was set on 70, one turned down to 60, one back up to 83 on cooling. I mean, there were just a broad spectrum. And then we said, well, who controls the building? Well, the building manager does. Well, who's that? Oh, well, you know, well, who tells them how to operate it? Well, they pretty well use their own judgment. You know, so you need to find out from the people how they operate the facility, and that's going to tell you how you're going to change the way they operate it, or you know, make administrative changes, because people don't always operate it the same. Typically, if it's a woman operating it, it's higher degree temperature on a general rule of thumb, because they're colder nature. If it's a man operating it, typically it's, I don't know, it's higher blood pressure we have or what it is, or just our irritable nature. But we typically have a cooler year-round. 5, when you get into facilities, that's where we come in. That's kind of our role. Expert, I don't like that term because that's a has-been and a drip. But consultants in this case, that's where we help you in the more complexities and the more nature of architects and engineers help on a consulting basis. Then the next thing we're going to do, once we understand, we know where you're at, we're going to look at things that you can do, calculate cost and savings, determine a priority list. That's where the city comes in, and then you actually start doing it, and then you monitor. Item 9 is the monitoring, and that's the most important, because you can brag on it all you want. I did a program in 1981. In fact, Ed Stone was with it. You know, we did this together with a firm we used to be with, and through the Department of Energy. It was a statewide competition for low-income housing for passive and solar. And people can't believe this. To this day, and people can't believe that this was accomplished, but it was accomplished. We had a 1,200 square foot house that it was calculated for 106 annual utility bill. Annual, not monthly, annual, in 1981. And the first year, and what we did is we didn't know how they operate a facility. Like, I mean, the variables that we can't control is washing clothes, drying clothes, how often they cook, how many kids, how many times they open the door. We have no idea. We control the things we can control. How in the spring and fall, do they open the windows, they close the windows, they have allergies. So what Ed did basically, we just did real good conservative sound engineering and calculated straight winter heating to winter cooling with no seasonal spring and fall opening windows, and theoretically that ought to get close to offset cooking, washing clothes, and that type of stuff, you know, kind of. Anyway, we calculated 106 or 108 annual utility bills. They actually used 112. One house was 112, I think one was 117 total annual bill, gas and electric for a year. But the way I'm going to relate that back to monitoring, after the first year, Department of Energy went defunct. We went from a Democrat administration to a Republican administration. I'm a Republican, so I'm not picking on them. But the different funding, different importance, they jerked the funds for the program. The people, it was a Farmers Home Administration. There's a lot of turnover. The economy, right after 81, went to. So what happened is the monitoring, there's no funding for monitoring. The program fell apart. The people who lived in the home moved because economic conditions. You move someone else in, they have no training on how to operate the facility. There's sun spaces that they had that were separated from the house. Well, they want that for square footage, so they take the doors out, you know, and open it up to the space, and now they get the direct gain in the summertime, which before they could close the doors off and open up the windows and vent it out through the attic. So they totally operated facilities wrong. One of them didn't like the way that all that glass is on the street frontage, you know, they're kind of like privacy, so they put evergreens up to separate from the house on the south side. Well, it just killed the solar collector, you know, which is nothing but windows. From the operation of the house. So monitoring and tracking the program is important as the design. In fact, more important than the design. You can be 10% off on the design, and if you at least track it at the end and keep control of it, you'll do something. If you have the best design in the world, the most accurate design, and you walk away bragging and strutting like banty roosters, as they say, and then a year from now you go, whoa, wait a minute, what happened? Oh, hey, this is supposed to do this. Well, monitoring is very important to track your actual bills consumption, because you may find out that there's a glitch somewhere. And again, that goes back to the operational, and that's why you talk to people, because you need to understand how they operated before and then how they need to operate it after. Because you may find out in the second 6 months of the first year or the second year, all of a sudden, you've had a mild winter compared to last year, but your utility bills are higher. Wait a minute. And then you get into it and you find out you're back in the old way of operating the facility. And we're not talking anything complex. It's just no one's doing their maintenance, no one's doing this, and that's what we find a lot of times, is people have habits and it's a tendency to slide back into bad habits. The next phase, after short break, okay, good. Everybody can stand up, go get the restrooms are through this door or through this.